Hey, just take a look around you for a second. The screen you're watching this on right now, the tiny chips inside your computer, maybe even the reflective coating on a skyscraper you can see out your window. They all have one thing in common. They're built with these unbelievably thin, perfectly applied layers of material. We're talking about coatings that are measured in atoms. And they're all made possible by this kind of hidden technology that, and I'm not exaggerating here, literally builds our modern world. So today, we're going to pull back the curtain on something called DC Magnetron Sputter.
All right, let's just jump right into the big question. How in the world do you paint with metal, one single atom at a time? I mean, how is it even possible to lay down a film of, say, titanium or a complex alloy so that it's perfectly uniform, impossibly thin, and covers every little microscopic nook and cranny on a surface? You know, it really sounds like it should be magic, but it's just pure physics.
And just look at this image. We're talking about coating features that are thousands of times smaller than a human hair and doing it with perfect precision. This isn't just for making things look pretty. This is the bedrock of modern microelectronics. Being able to evenly coat all these tiny little steps, it's a thing called step coverage, it's absolutely crucial. So, how do we pull this off? Well, the answer is in a process that's really less like painting and a lot more like a game of microscopic billiards. It's a method of what's called physical vapor deposition, and the technique itself is known as sputtering. Okay, so that's the official textbook definition. But what does it actually mean? The best way to think about it is to imagine a rack of billiard balls. Now, instead of a cue stick, you fire the cue ball at that rack at an insane speed, and what happens? Balls go flying everywhere, right? Well, in sputtering, the cue ball is a high-energy ion, and that rack of balls is your source material, what we call the target. We are literally playing a game of cosmic billiards to knock individual atoms loose.
Let's just walk through it step by step. So first you start with a vacuum chamber, and you pump in just a little bit of an inert gas, usually argon. Then you hit it with a high DC voltage. This ignites the gas into a glowing plasma, creating this whole cloud of positively charged argon ions. Now these ions see a negatively charged target, that's our source material, and they are instantly attracted to it. They accelerate and just slam into it with incredible force, physically knocking atoms of the target material loose. These newly freed atoms then fly across the chamber and land on whatever it is you're trying to coat, the substrate, and they build up, atom by atom, into a perfectly thin film.
And this diagram here, it just shows that moment of impact perfectly. You can see the positive argon ions, they're marked R+, just bombarding the target. And those atoms labeled M? Yeah, those are the material atoms being ejected or sputtered on their way to form that coating. It's a really simple idea, but it's so powerful. But, there was a problem. A big one. This basic version of the process, which is called diode sputtering, it worked, sure, but it was just painfully slow. I mean, way too slow to be economical for most commercial uses. So for a long, long time, it was mostly just a scientific curiosity.
And this timeline really shows you just how long it took for this to catch on. The basic effect? It was first observed way back in the 1850s, but it wasn't really used much until the 1940s, and even then it was a pretty niche process. The real game changer, the breakthrough that changed absolutely everything, didn't show up until the mid-1970s.
So what was that breakthrough? Well, it was the magnetron. This one innovation completely transformed sputtering from this slow, methodical lab process into a high-speed industrial powerhouse. And it's all thanks to the incredibly clever use of a magnetic field. And believe me, the difference was like night and day. Over on the left, you've got the old way. Slow, inefficient diode sputtering with really low deposition rates. But on the right, fast, powerful magnetron sputtering with incredibly high rates. This one single change took sputtering from being a pretty limited technique to the industrial standard that we absolutely depend on today. So what's the secret sauce here? It's all about adding permanent magnets right behind the target. See how they create those curved magnetic field lines right there in front of the target surface? That right there, that is the key to everything. So this magnetic field creates what scientists call an electron racetrack. What happens is, instead of just flying away, the secondary electrons that get knocked off the target get trapped in this magnetic field. They go into this endless looping path right above the surface. And as they race around and around, they collide with and ionize way more argon atoms than they ever would have otherwise. More ions means more bombardment of the target, which means, you guessed it, a dramatically faster sputtering rate. It's so simple, and it's absolutely brilliant.
Okay, so now we have this supercharged process. Let's take a look at the incredible results you get. And you'll see why this technique became such a powerful tool for engineers and scientists all over the world. The advantages are just staggering. I mean, you get incredibly high deposition rates, you can sputter pretty much any metal, any alloy, or even compounds. The films you create are extremely pure, and they stick with this incredible adhesion. It gives you excellent coverage of those tiny microscopic features we talked about, and because the process doesn't generate a lot of heat, you can even coat sensitive materials like plastics. On top of all that, it's easy to automate, and it scales up beautifully for huge surfaces like architectural glass.
So, it sounds like the perfect process, right? But every hero has a weakness, a kryptonite. And for DC magnetron sputtering, its kryptonite is any material that doesn't conduct electricity. This leads to a fatal flaw that we call the charge-up problem.
Okay, so here's the deal. The whole DC process relies on the target being conductive. It needs to be able to get rid of the positive charge from that constant stream of ions hitting it. But what if your target is an insulator, like a ceramic? Well, those positive charges have nowhere to go. They just get stuck right there on the surface and start to build up.
So what happens when you build up a layer of positive charge? Well, it creates this invisible shield. Any new incoming positive argon ions are simply repelled by it before they can even reach the target. And within microseconds, the entire sputtering process just stops, dead in its tracks.
So how do you get around this? How do you sputter an insulator? Well, you switch the power source. You go from direct current, or DC, to radio frequency, or RF. As you can see here, DC sputtering is the king for anything conductive. But for insulators, oxides, nitrides, ceramics, you need RF. By flipping the voltage back and forth millions of times per second, the RF field attracts electrons during one half of the cycle, and that neutralizes the positive charge that built up during the other half. It completely solves the charge-up problem.
And that kind of brings us full circle. The huge leap from a slow, niche scientific process to a high-speed industrial powerhouse, it was all because someone figured out a clever new way to apply a simple magnetic field. It just goes to show how harnessing a fundamental force of nature in a new way can completely change everything. And it leaves you with a final thought, right? If a simple magnetic field can do all this, what other fundamental forces are just waiting out there for the right person and the right application to unlock the next great technological leap?